Hello guys, today will be our last section, our last lab for this semester, and it will be about storm water management model, SWMM. So let's start by showing you how you can find this software. I will attach this link to the description of the tutorial, and you can click here to download the exe file, and actually the installation process is very easy. So once you finish with the installation, you will find this icon here, and you can click on it to start the SWMM model or the SWMM software. So let me give you a brief introduction about SWMM model before getting into the actual example that we will explain. Most of the time we use SWMM to simulate the sewer and storm networks, and actually we can use it to simulate both of them at the same time. And we already studied the open channel flow by using Manning equation, and actually what does SWMM model do is it just gives us the simulation or the solution of Manning equation for a huge number of network or a huge number of open channels that form complicated networks. So instead of doing the calculation manually to calculate the velocity and sometimes the normal depths, we can just use SWMM to do it for us. As you can see here, we have three main components in the SWMM software. We have the hydrology component, the hydraulics, and the quality component. Of course, the focus of this tutorial will be about the hydraulics component here, because of course this is the objective of the CME 211 course. So we won't actually speak a lot about the hydrology, and we are not going to speak about quality modeling at all. So why we use SWMM model? I said that we use it to simulate sewer and storm networks, and what I mean by that is, let's say that you want to get rid of some sanitary wastewater that have been collected or accumulated in several homes, or let's say that we had a rain event and now the streets are full of rainwater and we want to remove this water. So we use SWMM to build networks that gives us an understanding of what is the sizes, what is the slopes, what is the specs of the network that can actually get rid of this amount of water. So let me show you a very good picture that describes the process of training wastewater, if it comes from sanitary usage or from a rain event. On the left side of this image, we can see that there are two different types of networks: the storm networks or the storm system and the sanitary system. As you can see, the storm is linked to some areas with different land uses. In this area, for example, it's a car parking. In this area, it's an urban area, with some green area. And as we say, the storm network or the storm system is only concerned of collecting the rainwater, getting it inside the network and disposing it in a certain point. And of course, because the rainwater is very clean, we can just dispose it to any water body nearby. But for the sanitary system, most of the time we collect water from houses, maybe from other land uses, from like factories or so, and after doing that, the water will flow inside this network or this pipes, and then it reaches the wastewater treatment plant, which which does some kind of treatment before disposing it to a water body. We can merge these two systems into one, and if we did that, it will be called a combined sewer system, and the same process applies. It collects the water from different land uses, and sometimes it also collects the sanitary wastewater from houses. Merge or combine these two types of water, and of course it will be diverted to the wastewater treatment plant, then to the disposal water body. Great. So before getting into the simple example that we will see together or we will build together, let me show you how a full SWMM model should look like. Here is example number 1 in the SWMM examples, which shows a storm network model. And just to give you a brief overview about the hydrology part, the hydrology component, because in the SWMM we have 3 different components. The hydrology part, which is concerned in collecting the storm water, the hydraulics part or the hydraulics component, which we are going to speak a lot during this tutorial, and the quality component, which we are not going to explain that because it's not the purpose of this tutorial. So very briefly about the hydrology part. Any SWMM model that is built to simulate storm networks should contain 4 different components. It should contain the rain gauge, which simulate the rain event. It should also contain different catchments, which corresponds to different land uses. For example, I can say that this area here corresponds to maybe like a factory. This area is a green area, like parks also, and the other areas are urban, maybe schools, houses, or this kind of buildings. And the third component should be the junctions, which is the points that the water is disposed. Like this area here dispose its water to this point, this area to that point. So the junctions are the points that the water is dropped. Does not have like it does not have any other major importance. It only collects water. And of course we have the last component, which is the conduit component. And this is the main part in any SWMM model. We can describe the conduit as different as like open channels that are connected to each other. It can be in any shape. It can be circular, it can be rectangular, it can be trapezoidal, and you can actually select the shape of the conduit based on the actual case. Great. So as I said, this is the shape, or this is the shape of any complete SWMM model. Of course we won't be able to create a model like that because you don't have the knowledge of building a hydrological model, but also this won't be an issue because the hydraulics simulation won't matter actually if it is a hydrological model or a sewer model. And I mean by sewer models that we won't be concerned with this components. It won't matter. We won't have rain gauges and we won't have these catchments. We will only have the nodes and the conduits. And I mean that because I have removed the catchments, we will assign the wastewater loads as inflow directly to these junctions. Just imagine that we have a certain house here, and this house produces a certain amount of flow, maybe like 10 liters per second or so. So we won't use this catchments at all. Great, so after having this brief introduction, let's go through some tools that we might use or we will use and during building our project. I will start by creating a new project here from this ribbon, and the first thing that you should consider is the units that you are working with. We can use different units. We can use the metric units or the SI units, cubic meter per second, or the English units, cubic feet per second. And something to keep in mind that if you selected the cubic feet per second and you want to enter any area parameter, maybe like in catchments or any different components, just consider that the area will be in acres, not the square foot as you might expect. Great, so now let's create a very simple example, and I mean by simple, we will create this example here, except that we won't add any subcatchments or rain gauges as we said before, and we will only assign the loads directly to the junctions. Great, so there is a very good tool that we can use to insert this background inside our model so we can build the model while seeing it. We can select the location of the file, and here's it. You will see OK, and now we have the model, or at least the background of the model, so we can just start insert nodes and conduits. Before inserting nodes, let's take a look on the project defaults. And what I mean by defaults is when you start to build a model, you might have different objects. Most of the time, you should have the junction component or the junction object, outfall, and of course the conduits. So instead of having junctions that are named like 1, 2, 3, 4, it's a better practice to add a prefix to the junctions. In this case, we will use J, so it will be listed as J1, J2, and it will be O for outlets and C for conduits. Of course, there is no need to add any other prefix for the other objects. We won't use it anyway. That goes also for the subcatchments and for the nodes /links tab. Here we can set the default parameters. So let's say you have, in this case, we have 4 conduits, and the diameter or the geometry of the 4 conduits is the same. We can assign that here instead of selecting the shape for every different conduit. So we will use the circular shape, which is the typical shape of the pipes. Here we can insert the maximum height, which is the depth, and the number of paths, we will keep it as 1. Okay, so here we have the length, and to remind you, we are using the cubic feet per second, and this means that the length here is in feet, so no issue with that. The other important parameter is the conduit roughness. Actually, this is a very important value that you should understand. What does it mean? As we have the Manning coefficient and open channel flow or Manning equations, we have here the conduit roughness, and actually it corresponds to Manning coefficient. So most of the time we use the concrete pipes, which have a Manning coefficient of 0.013, We won't edit the other defaults, we will keep it as it is, and we can save these defaults for future or new projects. Great. At this point we have set the defaults, we understood the units that we are working with, and we can start adding some nodes and of course build our model. To do so, we can add the junction from here. I will press here to add the first junction, the second junction, third one, and the last one. And because we have black dots and the background is also black, we can like change the size of the nodes. In case if you couldn't see that, I have just clicked right click and entered options. Here I will increase the node size and the maximum is 9. Let's see if we unloaded the background. Yeah, it's here, so let's load the background again so we can put the output, which we can then unload it. Okay, so here we have the model again. We can insert the output, the outlet of this network, and we can now unload the background. So this is the major components of the network at this point. In case if I want to show the annotation, I want here to have J1, J2, and the same for the outlet. I can press that I want to show or display the node's ID, and it will be here. Great, so after this point we can add conduits, because to add conduits you will have to connect nodes with each other. So here we have the first conduit, the second one, the last conduit, so the third one, and the last conduit here. So now we have actually created a very simple network that might be a storm network if I have inserted the ring edges and catchments as in the picture that we saw already, or a sewer network by adding the direct inflow inside these nodes. So before doing that, let's see a very useful tool that we might use, which just in case if I want to assign a specific value for a certain object, we can do that by using the global edit. First I will have to select all, then I will go back to edit, group edit. So it asks you here which is the object that you want to edit. Okay, let's say that we want to edit the conduit. What do you want to edit? I want to change the maximum depth and to replace it with, instead of using 1 feet, I will use 2 feet. So this is a very useful tool that I can use. So let's enter, double click on the first conduit, and you will see here that we have the maximum depth changed to 2 feet. Great, so the next step would be adding the inflow. So as we said, there are two types of two ways to enter the inflow. The first one is by inserting a certain ring gauge like that, and catchment like that, and connect the catchment somehow by this node. After receiving the rain from this ring gauge, there will be some hydrologic process and calculations, and then the amount of water that has been collected will be assigned to this node. So this is not our objective in this tutorial, so I will just remove these objects and I will enter the junction itself to see how can I assign the inflow. So for a certain junction, you can see here that it has its name, its coordinate, if it has a certain inflow or not, if it's a treatment point, the invert elevation, maximum depth, initial depth, and very specific components. The main three components here are the inflow, the invert elevation, and the maximum depth elevation. Great, so for the inflow, we can see here that we have direct, tri-weather, and another tab that is related to hydrological process. So what we can do here is using the tri-weather just to assign the amount of flow that is added to this node. So how does it work? Just imagine that we have a certain house that produces 5 liters per second on average. So do you think that amount of water that is produced by that house will be constant with time, or it will vary with time? Actually, it will vary with time. So let me show you like what I do mean by that. So just imagine that I have a certain house here, and that house like produces a certain amount of flow or wastewater flow, and this wastewater flow should look something like that. We have here the time, we have here the discharge Q, and I have just said that on average this house produces, let's say, 2 liters per second during the day, like from 12 a.m. to the next day 12 a.m. Of course, during the night period, the water production will be very small, might be like less than 2 liters per second, until we reach like 6 a.m. You woke up and you want to go to school or to the university, the usage of the water will increase, or like the production of wastewater will increase. And after doing that, maybe at 6 p.m. you come home, take a rest, and the flow will be also reduced to a very small amount. So this should be the shape of the wastewater pattern that is produced by a certain house, and we can actually simplify that to a more simple shape, something like that. And what we actually give to the swim model is the shape of the red line. I can say, okay, the average is 2 liters per second, but we have a certain pattern, and that pattern starts by 0 because we don't have anything, and then it reaches half, or let's say quarter of the 2 liters per second. At 2 a.m. it reaches 0.9 or 0.8 the 2 liters per second, then it reaches twice 2 liters per second, and like that. So we can here enter here the average value, which is 2, and we can assign a pattern. So let's say that the pattern, of course, it should be hourly, and it starts by 0, then like 0.4, 0.8, then it reaches 2, stays like that for a while, then it comes back to 1.5, and you can do that until you reach the same, the end of the day, it reaches 0. So this is the pattern of the inflow and the average inflow, and we can do that for the other nodes. Let's say that a bigger house is connected to this node here, and the pattern is the same. Here we have a school with average of 12 cubic feet per second, and we can create another pattern. Actually, we can say this is a pattern, and this one for the school. We can use different values, different multipliers, and finally we can do the same for the last one. Great, so at this point we have entered the inflow, and it is direct inflow. And why I mean dry weather? Because it's not something related to wet weather. There is no rain in this situation. Great, so at this point we have entered the inflow. The next step will be entering the invert level and the maximum depth. Great, so what is the invert level? Okay, just imagine that we have a profile for the ground at this point. It's something like that. So this is the ground level, and of course under the ground we have the networks or the pipes, and between these pipes we have the nodes, that acts as the manholes or the points of entrance. Because if we have like a certain house here, and that house produces a certain amount of water, this water will be entered through the manhole, another one here, and another one here. So, and maybe like a certain discharge here. So what I mean by the invert level is it asks here the invert elevation or the invert level. Basically it is the elevation of this point. It is the elevation of the lowest point in the manhole, which then will be connected to this pipe here. We have also an invert level for every manhole. So to decide or to define the manhole, you should, or the junction, you should define the invert level, because the orientation or the slope of the pipes connecting each two junctions will be determined based on this invert level. And of course, because we are dealing with open channel flow, we can only use pipes that is sloped to a certain point. You can't have pipes that looks like that, because we depends on gravity flow. So these pipes should point like downhill up to the outlet. Great, so this is the invert level, and of course if you want this manhole to drop water to this point should have a higher elevation. So let's say that we have here an invert level of 25 feet. this point should have less elevation. Let's say that it's 20, and because J2 will drain its water to J4, this one should has a different or a lower elevation. This should be more than 18, it might be 22, and because this is our outlet, of course it should have a very low elevation. So after assigning the elevations, let's try to see a profile plot for the network that we have. And to do so, you can select the junction, and it would be your start node and this junction. End node, ask it to find the path for you, and press OK. So now we have the same shape. We have conduits that are pointing to a certain point. Great. As you can see here, there is no ground level because we didn't enter the maximum depth yet. So the maximum depth is the amount of ground that is above a certain invert level. So basically it is the offset between the ground and the invert level, and typically it can be between 4 and 6 feet. So we can use this range. We can say that it's 4 feet here, 6 feet in this node, 5, and here 6 again. And for the outlet, as you can see, there is no invert level because it won't affect anything for the outlet. Great, so let's see the same profile again. As you can see here, it shows now the ground level. Great, so up to this point we have almost created our model. So let's make sure that everything is settled. We don't need to enter any other data for the conduits. And the next step will be checking the simulation options. So let's click here on the option tab. As you can see, there are different models, of course, and because we only have the nodes and the conduits, we won't be able to make any snow melt or groundwater or water quality analysis. This bar here, or this tabs, asks you for the routing model. Most of the time we use the dynamic wave method because it produces a more accurate results, but in some cases we use the kinematic. I don't think we use steady flow because it's very basic and it won't give us the results that we want. And of course these are very specific details that are not related to the course, so we will just skip it for now. The most important tab is the dates tab. As you can see here, the start analysis, the start reporting, and the end analysis dates are almost the same. So just in case you have run the model, you want to produce a certain time series for the lateral inflow, you won't see anything. You will see that it shows you that the time series is always 0, and that's because we should do something here in the dates tab. Okay, starting analysis date. Actually, for us, the specific date does not mean anything, so you can select any date you want. start voting date, it will be the same as the start analysis. And here is the important tab. It asks us here about when do you want to end the analysis. Like, do you want me to make the simulation for 1 day, 2 days, 1 week, 1 month? That is very specific, and we, for this model, we can, 1 day would be enough. So I have increased this point here to 29. So the analysis will start as in 28th and will end after 1 day. So let's run the model again. It shows here something called continuity error, because we are, as I said before, here the SWMM model tries to use Manning equation to make the hydraulic calculations, and of course it should it can have some kind of error. So now I want to see the results of the amount of water that is added or loaded to these 3 nodes. I can go to the outlet and produce a time series for the lateral or the total inflow. So I will press accept, and as you can see here, this is the flow pattern at the output or at the outlet node. And of course, based on that, I can say, okay, at this point we have a very huge amount of water coming, so if I have a wastewater treatment plant, I will have it to work with a high capacity at 5 a.m. But after maybe like 7 hours, or I mean like after 3 or 4 hours, it might work with a lower capacity. So the amount of the total inflow at the outlet is very important, and also I can see how a certain conduit acts. That can be done by plotting a profile for every conduit, and I can, using this map here, I can scroll to see what is the performance or the water depth at every time step. And also I can make like a simulation by pressing the play button here, and of course if the speed is very high, you can see the water depth varies, because of course the amount of water that enters the J1 node is different with time. So we can also use this tab here to show some of the results. We can say that we want to show the flow of the water flow inside every conduit, and of course the default of course, because the flow at this point is like almost similar, every node or the conduits have the same color. So to edit that, I can click here, right click, and ask it to make an auto scale for me, then okay. So now you can see that this tab, okay, let's make it clear. Let's use the red line, the red color. So now we can see that for these these 3 conduits, the flow is around 4 cubic feet per second, and of course for the last conduit the flow is huge, it's around like 12 cubic feet per second. Based on that, and because I'm trying to design this network, I can say, okay, because this pipe here has a greater flow, I can make its depth larger, or I can use a different shape. So this is the main point of making a simulation model. You want to know or you want to understand how your network will perform under a certain condition. Of course, this is a very simple project, this is a very simple model, but if you understood the ideas or the concepts behind this model, you should be able to create a more complicated one. Okay, thank you.